Okay, so in this segment, I'm going to just focus on giving you a few examples on fatigue design to illustrate how we can combine the mean stress and the alternating stress in estimating either the factor of safety, which is one thing that we would like to know for an infinite fatigue life, or if desired, we want to find the number of cycles to failure having the combined mean value of the stress and the alternating. So the first example that you see here is 1.5 inch diameter bar, and it's machined. So the surface finish is been machined from IC 1050 called drawn bar, which means that I can go to the tables and find the ultimate strength for IC 1050 and the yield stress as well. And this bar, it is to withstand the fluctuating tensile stress varying from 0 to 16 kip, which means that I can find the minimum is 0 and the maximum is 16. And because it is axial loading, is the simplest type of loading, I can determine the basically the cross-sectional area, divide the minimum value of the stress by the cross-sectional, the minimum value of the load by the cross-sectional area gives me a sigma min, and I can do the same thing for sigma max to determine both of them. Once I know sigma min and sigma max, I should be able to determine the alternating component of the stress and the mean value of the stress. Now, this is not the end of the story because we have here to consider also stress concentration. So we have a fatigue stress concentration factor. Luckily, is given to us 1.85. In some cases, if it's not given, then I have to go from K sub T, which we discussed it before. That is actually the essential stress concentration factor under static loading. And then if I know the notch sensitivity coefficient Q, I can find K sub F. But here it is given to us as 1.85. So first we want to find the S alternating and S M, which, or you can say sigma alternating and sigma mean. And then we want to find the factor of safety guarding against two things, fatigue and first cycle yielding. First cycle yielding, meaning we don't want to go above the Langer line. And what we want to do is we want to use Gerber first, fatigue line, and ASME after that, ASME elliptic fatigue line. So in this example, you see that I have the forces, minimum and alternating and mean. And before I go there, I need to apply the Marin factors to the endurance limit, so I can convert the rotating beam endurance limit to the practical one that I'm going to use in the design. So the first factor, K sub A, is for the surface finish. So we use the equation 619 and gives us 0.797. And then the second factor is for the actual size. So K sub B should be for the size. So they did a little mistake here, but you can use the equation for the size effect that we discussed before. And then the third factor is for the loading, and the loading is axial, so it's K sub C is 0.85. And then the other factors, the D, is the temperature factor. We are not given any information, so we use it to be 1. And E is the reliability factor. So for the reliability of 50%, we're going to use also equals to 1. And then miscellaneous factors equal to 1. If we're given those, we should apply them. But eventually, we convert from the endurance limit that we have to the for the rotating beam to the actual endurance limit that we're going to use in the design. The point that I wanted to make also here that you note is that we are not given the endurance limit SE prime. So what we're given is S ultimate. So we have to use this correlation that it is SE prime is approximately 1/2 times S ultimate. So you have 1/2 times S ultimate. This will be SE prime, and then the rest are these are the Marin factors that gives you 33.9 KSI for SE that we're going to design for. Next step is we find the nominal values as we mentioned, nominal. So the nominal are 0, so the subscript 0, and this is far away from any disturbance. So the idea here for the nominal is that we assume that we don't have any stress concentration. First, calculate the stresses, and then when we use them in the design, we amplify the nominal by the stress concentration factors. So the nominal is the force divided by the area, gives us, for the alternating, gives us 4.5. KSI for the mean gives us another 4.5, the same. And then the actual alternating goes from the nominal converted to the actual alternating with the stress concentration factor, which are given here 1.85. So all of a sudden I have now the mean value is equal to the alternating value is equal to 8.38, and that is at the shoulder that we were considering, because they asked us to look at the fillet at the end, and that has a fatigue stress concentration factor. So having done that, then first we wanted to, if you look at the problem, we want to compute, we want to find the factor of safety for Gerber and for ASME. So the factor of safety will go back to the equations for Gerber. This is the factor of safety for Gerber is right here. So it's we know now the ultimate, we know the mean, we know the endurance, and we know the alternating, and therefore we can substitute in this equation and find actually all of the parameters will lead to the determination of the corresponding factor of safety, and that comes to be 3.66. Now the next is to guard against first cycle yield is we solve for the Langer line, the intersection of the Langer line with the load line, and that gives us 5.01 because we are solving for the intersection between the load line and the Langer line here to give us the factor of safety. If we look at graphically what we've done, like right now we've done everything here mathematical. So if we look at the graphical representation, then as we mentioned, we have to show where is the load point itself on the load line. So this is, we're going to call it point A. And then we want to show the intersection between the Gerber line and the load line, call it B. And then the intersection between Gerber line and the Langer line, let's call it C. And the intersection between the Langer line and the load line is D. So we have like 4 points to show on the graph due to this solution. So if we look at this, we see that this is the load line, and the load line, this is the actual load point where the mean value of the applied of the local stress is 8.38, and the alternating value is 8.38. And then if I look at the load line to be, we know that the load line is S alternating over, or let's say in this case we're going to call it sigma alternating divided by sigma mean is equal to R. and in this case R is equal to 1 because the alternating is equal to the mean, and that is the load line, as you can see here. Now there's an intersection between the load line and the Gerber fatigue curve at point B. There's another intersection between the load line and the Langer line at point C. And then there's an intersection between both the Langer line and the fatigue line at point D. And we have the equations to solve for the coordinates of all of these. So point B has the coordinates as 30.7, point C has coordinates of 42 and 42, point D has the coordinates of 64 and 20, and those are obtained from the Gerber equations, where we have, this is one point, as you can see here, this is the second point, this is the third point that we can obtain from the graphs. And that basically, we can program that and determine the factor of safety. The point also that I wanted to mention is the factor of safety. If we have an operating point here, the factor of safety for fatigue will be the ratio of this length divided by this length, which is equivalent to saying that this is exactly the same, because of triangular similarities, exactly the same as the ratio of this length divided by this length, or this length divided by this length. All of these are the same as the safety factor NF. This is the fatigue safety factor. The yield factor, safety factor, the safety factor against yield on first cycle is the ratio of this length divided by this length, and that is the 5.01. This ratio is pretty high. And or you can have it as the ratio of these two lengths, or equivalent to the ratio of these two lengths. All of these give you 5.01 that was computed before using the simple equation that we found here. So we have 5.01 for the yielding guarding against first yield, or 3.66 guarding against fatigue on any cycle. We could do pretty much the same for the ASME, and I think I'm going to let you do that, where we can find the exact, here's the ASME, for example. We can find the factor of safety. It's a little bit slightly different, 3.75, and you can also represent it graphically, where the ASME is elliptic, and then you have these 4 points. This is the load point, this is the load line versus fatigue line, this is load line versus Langer line, this is Langer line versus ASME point, and we have the equations to solve and determine factor of safety. And one factor of safety, as we mentioned, would be this ratio. This is the fatigue factor of safety, and the other one, factor of safety, is the first yield factor of safety, which is this ratio, as we mentioned before. So we'll come pretty close to what we've done before. The next example is actually kind of a more more realistic design example, in which we want to design a CAM follower system. And the CAM, as we know, it kind of is a plate that has sometimes is a complex shape to give you certain motion for the follower. But if we have the simplest case here, is that if we have a circular cross-sectional plate, but it rotates not about a center, it rotates about an eccentric point, then as the cam moves, you can have a follower, and the follower can move up and down to follow that cam. So this is a design problem that we would like to read together and then complete the design. So let's consider it here. So in this design, we have a flat spring leaf, flat leaf spring, and this is the leaf spring, as you can see here. It's 2" by 1/4 of an inch by 32". So we have all of the dimensions of the leaf spring. And it is used to retain an oscillating flat face follower. So this is the follower, it's a flat face follower, and this is the cam. So the cam has an eccentric rotation point here, and this rotation point can move up or down. So if we push this point down, for example, then there will be an initial deflection of the spring, and the initial deflection is given to be 2" for slow speeds. If the cam is going to rotate very fast, then the initial preload is recommended to be 5", and this will guarantee that the follower is not going to jump and has a lot of inertia that can jump up and down. So the design problem, as we have here, is that we want to design this system we want to design the spring, the leaf spring itself for fatigue design, which has the ultimate strength of 150, the yield is 127, endurance limits given to 28, fully corrected, so we don't have to worry about the Marin factors here. And it says that the total cam motion is 2", meaning that if the cam is like this and it's rotating about this point, then the cam can move like this. So it's moving like that. Then from here to here is 2". This is 2". This is the total cam motion, meaning that this is going to go up and down 2" as the cam rotates around. So the cam design is such that we have two things. We have an offset from the beginning that can be 2" or 5", and we have motion, which is the up and down motion is 2" to be added to the offset. In other words, we want to design the system for two problems. One is 2" offset, and the other one is for 5" offset. And we want to plot the Gerber-Langer line, failure lines, and the load line. And we want to find the factor of safety corresponding to the 2" case and also to the 4" case. So in this situation, let's start by finding the relationship between a deflection. First, I want to find the deflection. What does it mean in terms of a stress? What is the stress? So the stress is going to be a bending type stress, and we know the deflection, and we want to find the stress. So the first part of this problem is that given that you have a deflection, what is the moment that caused the deflection? Once we know the moment that caused the deflection, is what is actually the corresponding stress that will correspond to the deflection. So as the deflection goes up and down by 2", then the stress is going to also oscillate with that, in addition to the mean value that is applied. So let's go here to get to the stress. We find the moment of area, second moment of area, BH cubed over 12. We get the value. Now we find the relationship that we've discussed from the deflection, cantilever deflection in one of the previous sections, that this is the force that causes deflection Y is given by 3 EI times Y over L cubed. And the force times the distance is equal to the moment, and therefore and the stress is equal to the moment times C over I. So we can do this calculation and find a relationship between the stress and the deflection Y. The K is a factor that combines everything here except the Y, and this we can compute and find that it is 10.99 KSI per inch. So it means that every time there is a deflection of 1 inch, we need about almost 11 ksi of, or it produces, it corresponds to a stress of 11 ksi. So as the cam moves up and down from 0 to 2 inches, then you go from 0 stress to 11 ksi. And therefore, we wanted to find kind of the maximum minimum stress. We have to find the minimum deflection and the maximum deflection. The minimum deflection is going to be the sum of the offset and the motion. And the motion can go from 0 to 2 inch. So we have the minimum is delta plus 0, the maximum is delta plus 2 inches, and therefore sigma minimum, you multiply by k, you get a value of the minimum and maximum stress, and therefore you can get the alternating stress and the mean stress, because we know now all of the parameters. We only left delta to be in a parametric form because delta is the offset. So we have offset 0 offset, 2 inch offset, 5 inch offset, and that gives us the alternating under these three conditions. The mean is the same. Mean is the same as the alternating, and sorry, the alternating is constant at 11 ksi, but the mean will change as the delta, the initial delta, will be also changing. So if we look here graphically on the solution, we have the Langer line. This is the 45-degree Langer line from yield to yield. This is your Gerber line, and this is the load line. The load line has an offset of 0, an offset of 2, an offset of 5. And this is a horizontal line because the alternating doesn't change, because the motion of the cam does not change. It's the same cam, so it will be moving on a horizontal line. So having said that, and if you look at the intersections that we need, you find that they're pretty crowded right here. So you get the intersection between the load line and the Langer line, and the load line and the fatigue line. When we work out those, we find that the result is we have 116.9 ksi for the first point, which is right here, and then we could work out also the intersection for the second point. We'll find that it is 116. So it means that fatigue and first cycle yield are approximately, the threat is approximately equal because the intersection points are pretty much the same. And then we can find the fatigue factor of safety for delta equals 2 and the fatigue factor of safety for delta equals 5. That it turns out to be 3.54 for delta equals 2 and 1.77 for delta equals 5. And again, we can find the factor of safety against yield by solving the Langer line with the load line. So with this, I think we have covered a very good example, and it tells us that we need to be very detailed when we solve a problem that involves the maximum stress can exceed actually the yield to guard against yield on the first cycle. The last example that I'm going to have is an illustration of what you do if you want to design not for an infinite life but for a finite life, and that's an important example. So in this example, I have a steel bar, and the steel bar undergoes cyclic loading. The maximum is given 60, minimum is given minus 20, and it has a material as the ultimate 80, and the yield is 65, and it's fully corrected. The SE is equal to 40, and the F is equal to 0.9. So we can use approximate formulas for the SN curve as we learned before, and we want to estimate now the number of cycles to fatigue failure. And we're going to do that using modified Goodman and using Gerber. So first step, calculate sigma alternating, sigma mean. And then second step, if we have modified Goodman, we find the corresponding fatigue factor of safety, 1 over this, and gets 0.8, which is less than 1. It means that we have to stop. Stop. Why? Because this equation here is based on an infinite life. Therefore, for an infinite life, we get a fatigue factor of safety of less than 1. Therefore, we need to actually go now and design for a finite number of cycles, since the safety factor is less than 1. And we'll do that by making a certain correction. So remember that we have sigma alternating over S endurance plus sigma mean over S ultimate is equal to 1. This is the damage due to alternating, and damage due to the mean equals to 1. That's kind of the modified Goodman idea. Then we want to, this is for infinite life, infinite. So we want to mimic the same idea but for finite. So what we'll do is we ratio now the alternating not to the endurance limit, but to kind of an effective equivalent stress that is reversible, like what we call it sigma R, sigma rev. So we would modify it by saying sigma A divided by sigma REV instead of the endurance. This is for a finite life, not for infinite. Plus sigma mean divided by SUT is equal to 1, and solve for sigma REV. And sigma REV is like the equivalent alternating stress when we have an additional damage component due to the mean stress. And you can see here the sigma REV is 53.3, which is higher than the alternating stress. And the reason it's higher is that it accounts for some additional damage due to the mean stress. In other words, we would kind of pretend that we don't have a mean stress because we took its effect on the alternating by modifying the alternating and making it actually higher than what it is, and then use now sigma REV instead of sigma alternating in all our designs. And that's the case here because we could use the power law equations for A, F S UT over SE. Gives us a value, and for B, so we give another value. So this is basically, once we get A and B, then we would know the equation for the power line that describes N as a function of sigma. And it used to be sigma alternating. Now, because we have the mean, we're not going to use sigma alternating, but we're going to use sigma REV. And sigma REV reversible is higher than alternating by a little bit. So instead of 40, it goes to 53.3. And therefore, the number of cycles to failure can be estimated to be 3.4 times 10 to the 4. That's 34,000 cycles until we get failure. So these are basically examples that cover the wide range of how to combine the mean stress and the alternating stress in various designs. Once we specify what kind of fatigue criterion we would use, and also once we decide whether we would have an infinite lifetime or a finite lifetime for a component.